I'd like to introduce the performance of atmospheric models on low-cost GPUs and HPC-grade high-performance processors. So our model is a specific type of atmospheric simulators, and it's a combination of a global low-resolution model and high-resolution model. However, the low-resolution component is computationally very lightweight, so let's focus on the high-resolution model, which takes care of small-scale processes like clouds. And here we need a large number of vertical two-dimensional high-resolution atmospheric model solving the Navier-Stokes equation and radiative transfer, etc. We adopt an existing atmospheric model called ScaleRM, developed by the RIKEN Research Institute in Japan as the high-resolution component of our model. And the original ScaleRM model is designed for three-dimensional atmospheric simulation. However, we need, for our model, a large number of two-dimensional domains. So I hijacked the y-axis of the original model and use it as a domain number, so we can perform two-dimensional domain in large numbers. And as I said earlier, we exclude the global component for now and focus on the high-resolution component ported to the GPUs. The global component, if active, would run on the unused CPUs on the GPU-equipped machines and does not affect the performance. So the first thing we need to keep in mind is to minimize the data transfer between CPU and GPUs. The CPU takes care of the main loops and runs the GPU kernels. On the other hand, the GPU takes care of almost all array operations, and we make sure that almost no data transfer occurs during the main loop because that data transfer is relatively slow. And some previous studies employ the unified memory technology. However, they noticed some initial latencies associated with the unified memory. So we decided to explicitly handle the data residence using the ACC data directives. And our model often contain huge horizontal loops containing hundreds of lines of code, like subroutine codes and vertical loops. And it was very difficult to parallelize them well on GPUs using the OpenACC. Probably because the registers were not enough. So to improve the performance, I split loops to simple ones, collapsible ones, and moved subroutine codes outside of the horizontal loops by modifying those subroutines to handle three-dimensional data instead of 1D. And so all kernels handle simple collapsible loops rather than very complex loops containing hundreds of lines of code. This modification required me a lot of work in modifying almost all codes of the model. However, it allowed me to get some reasonable performance consistently, easily on using OpenACC. And another aspect of the model is that all kernels are very light, short, so no kernel is dominant. We have hundreds of GPU kernels launched every time step in milliseconds, and none of them occupy more than 5% of the total execution time. So we cannot tune one kernel and improve the performance of the whole model significantly. Rather, the total typical kernels run for around 20 microseconds. So the initial launch latencies really add up and slow down the model. So we really do not want to launch the kernels synchronously with respect to CPUs. So instead, we launch the kernels asynchronously. So we hide the kernel launch latencies. And we have two options for the asynchronous execution. One is to launch kernels async in multiple queues, so we can launch kernels simultaneously and save some time. However, launching multiple kernels simultaneously makes the problem of data dependencies among kernels. If one kernel depends on the results of other kernel, then we may have to make sure that the kernels do not run simultaneously. So we have to divide kernels into blocks of independent kernels and do ACC weight among the blocks of the kernels. And this ACC weight and the kernel runs take some time and cancels out the performance benefit of the multiple simultaneous execution. So we really do not want to keep track of all data dependencies and rather decided to use only one queue. Here we launch kernels asynchronously with respect to the CPU, but sequentially on the GPUs. In this way, all kernels runs sequentially, so we do not need to keep track of inter-kernel data dependencies. So the implementation is much easier. And the execution time is almost the same as the multiple queue option. As far as I know, this feature is not available in OpenMP GPU offloading. So we really like this fine control of the asynchronous execution in the OpenACC, and this is a big reason to choose OpenACC for our AtomCX simulation featuring a large number of small kernels. Okay, let's move on to the performance test. We have a large number of vertical two-dimensional atmospheric domain, and in all simulation with the double precision, here we have multiple processors from HPC grade high performance GPUs, HPC grade CPUs, and even lower cost GPUs, consumer grade GPUs from the personal computers. The problem size suitable for those processors are very different. So it is difficult to evaluate the performance on those processors in a fair way. Here we decided to choose the number of domain, two-dimensional domain, so that the total simulation times are more or less similar among all the processors. So we compare the number, the gigaflops achieved rather than the simulation time with the same number of domains. Here is a test result as shown in the table. We show the plot in the next slide. The right one is the estimated throughput of the atmospheric model. And the estimated throughput is much lower than the theoretical values because our application is really memory bound, so we cannot fully utilize the calculation capability of the processors. We can see clear relationship between the theoretical memory bandwidth of the processors and the estimated throughput of our model. The blue ones are Intel CPUs, Xeon CPUs, and we can see that the proportional coefficient is larger on those Intel CPUs, probably because the latencies are very small on Xeon CPUs. On other processors, the performance is proportional to the memory bandwidth, and we can see that the small n, the NVIDIA's lower cost GPUs perform very reasonably it's proportional to the memory bandwidth. Even though the capability of those GPUs for the double precision floating point operation is minimal. Our application require very intensive memory bandwidth, so we can fully utilize the memory bandwidth of those processors, and the performance is really reasonable. This means that the lower cost GPUs, even GeForce consumer grade GPUs on gaming PCs, could be very useful for small scale development purposes. In fact, those Intel CPU, the values are from 2 sockets of the Xeon CPUs. So if you compare 1 socket of the Xeon CPU and 1 GPU of the GeForce RTX 3060, the performance is almost the same. So those consumer grade GPUs could be really cost efficient for small scale development. For high performance computing, the power consumption is sometimes really important. Even though the Xeon CPUs are very fast, they require a lot of electricity. So the performance per watt is not very high. In contrast, the A64FX CPU by Fujitsu on board the Fugaku supercomputer in Japan, this CPU is much more power efficient, and the performance per watt is more than twice as much. And on the top of that, the A100 GPU is even twice as energy efficient as the A64FX CPU. In Japan, often the size of the supercomputer is limited by the amount of electricity that can be supplied. So this indicates that the GPU is really suitable for atmospheric simulations when the computational size is limited by the power consumption. Finally, let's compare the performance of the latest generation H100 GPU and the A100 previous generation GPU. I was not able to measure the power consumption of the host for this comparison. For this, I included the person consumption of the host system as well. But here, let's focus on the GPU power consumption. And we can see that the performance per watt is not better on the latest generation H100. One reason is that only the H100 we use is air-cooled, so the GPU temperature is higher, so the leakage power is also higher. However, even if this H100 was water-cooled, I think that the performance per watt is almost the same. I mean, it's probably because this flavor of the H100 we use is optimized for floating point operation rather than memory bandwidth. So our memory band application could not perform too well. So instead, we expect much better performance per watt on different flavors of H100 featuring faster memories. So to summarize, I ported the atmospheric model to GPUs using OpenACC, and I really like the fine control of the asynchronous execution features made possible by the OpenACC. And the consumer-grade GPUs perform comparably to Xeon CPUs, so this would be a cost-efficient platform for small-scale purposes. And HPC-grade GPU is very energy efficient. And we expect even better results on flavors of H100 featuring faster memories. Okay, that's it from me. Thank you very much.